Our discussion is on shearing stress. So forces parallel to the area resisting the force cause shearing stress. So basically, shear stress is a force tending to cause deformation of a material by slippage along a plane or planes parallel to the imposed stress. So it differs to tensile and compressive stresses, which are caused by forces perpendicular to the area on which they act. So shearing stress is also known, or it can also be called as tangential stress. So the formula that we will be using for shearing stress is equal to tau to represent shearing stress, which is equivalent to V all over A. So V is the resultant, this one is V is the resultant shearing force, and A, of course, is the area which is being sheared. So for a shearing stress, if we try to apply a force on a certain plane, for example, this illustration, so you applied a force, you have two planes, so being attached by a bolt. So if we're going to apply a force on each end, on both ends of the plane, so this will be sheared off. So this portion will be sheared off. So this illustration is what we call single shear. So we have also our double shear. So this one is an illustration. The second one is an illustration for a double shear. So if we try to apply a force at both ends of the plane, so this portion will be sheared off and this portion will be sheared off. So that is why it is being called as double shear. Problem number 1. What force is required to punch a 20 mm diameter hole in a plate that is 25 mm thick? The shear strength is 350 meganewton per meter squared. So we are given here with a figure. So what is being asked of this figure is what will be the force that is required to punch this 20 mm diameter hole. So that is the force unknown is denoted by P. So basically for this illustration, the resisting area is this one, the shaded area along the perimeter, and the shear force V, of course, is our P. So you have to take note that our V is our P. So of course the formula for shearing stress is equal to shear force all over the area. And of course our shear force is equal to our P. So if we're going to solve for P, which is the force that is required to punch in our 20 mm diameter hole, so our given for our shearing stress, the allowable shearing stress is 350, and of course this is equal to our shearing force, which is our V, or equivalent to P, and all over our area we are given with a 20 mm diameter for this hole, so therefore our area for this is equivalent to the diameter times pi times the thickness. So this is the punch out. This portion is the punch out, and it has a thickness of 15 mm, and of course it has a diameter of 20 mm. So therefore the area will be pi times 20, which is diameter, multiplied to the thickness, which is 15. So if we try to simplify this one, you get a value of 549,778.7 Newton, or this is equal to 549.8 kilonewton. So that is for this particular example. Problem number 2, as shown in the figure, a hole is to be punched out of a plate having a shearing strength of 40 kSI. The compressive stress in the punch is limited to 50 kSI. Letter A, compute the maximum thickness of plate in which a hole 12.5 inches in diameter can be punched. Letter B, if the plate is 0.25 inch thick, determine the diameter of the smallest hole that can be punched. So we have our figure for our problem. So we're going to punch at a certain force peak. So what will be the value for our what will be the value of the thickness of the plate, and what will be the diameter of the smallest hole that can be punched out. So basically for our solution, so to start with, to get the maximum thickness, we're going to have letter A, our thickness of the plate. So this is denoted by T. So based on puncture strength, if we try to base on puncture strength, we're going to have, of course, the formula P is equal to sigma multiplied to the area. And our allowable strength is equivalent to 50 KSI based on the puncture strength. So this is 50, then multiply to the area, which is, it has a diameter, we're giving it a diameter of 2.5 inches. So this is 5 over 4 times 2.5 squared. So if we try to simplify this one, we get a value of 78.1255 kips. So this is the equivalent shear force of the plate. So this is our equivalent shear force of the plate. And based on the shear strength of the plate, so if we try to have the formula for shearing stress, of course, tau is equal to V all over A. And we are given now, of course, this can be equivalent to V is equal to tau times the area. Of course, we have computed our shearing force, which is equivalent to 78.1255 kips, equal to our shearing strength for this one is limited to 40 KSI. Then multiply to the area, and the area for this, since you are given with a diameter of 2.5, so this can be pi times 2.5 multiplied to the thickness, and the thickness now is equivalent to 0.781 inch. So that is the thickness for the plate. Now for letter B, if we're going to have compute for the diameter, so diameter of the smallest form. So if we're going to have based on compression of puncture, so of course P is equal to stress times the area. So based on puncture strength, our stress is equal to 50. So simply have to substitute, multiply to the area, which is pi d squared all over 4. So we have now our, this one is our, if we try to simplify this, you can have 12.5 pi d squared. This is now the equivalent shear force of the plate. If we're going now to compute for the diameter based on the shearing of plate, so we have P is equal to stress multiplied to the area. So therefore, you substitute the equivalent shearing force, which is 12.5 pi d squared is equal to 40 times pi d multiplied to the diameter, to the thickness, which is 0.25. So if we try to simplify this one, we get now d, which is equivalent to 0.8 inch. So that is now the value for the diameter, which is 0.8. The thickness for the first unknown is 0.81 inch, and for the second unknown, which is the diameter, that is 0.8 inch. Problem number 3, compute the shearing stress in the pin at B for the members supported as shown in the figure. The pin diameter is 20 mm. So for this one, we are given with our figure and we have to identify. So this is our point B, this is our point C. So we have to identify the reaction forces. Of course, we have a roller, so this one is, you have a vertical reaction force, that is RC. This one, we have a pin support, so reaction forces, you have horizontal, R's of BH, and of course R's of BV for the vertical. So for this, we try to identify first. We're going to solve for the shearing stress at point B, so we have to identify the reaction at point B. So let us solve for the reaction at point B. So let's have summation moment at point C equal to 0. So therefore, we can have here, this one is a counterclockwise direction. So we're going to have negative R's of BV multiplied to the moment arm distance, which is 0.25, then plus this one, you have 40 kilonewton, you have horizontal and vertical components, so that will be plus in a clockwise direction, 40 cosine of 35 multiplied to 0.2, then plus 40 sine of 35, this is times the moment arm distance, which is 0.25, equate that to 0. So if we try to simplify this one, will be a component for our reaction at point B is equal to 49.156 kilonewton. So now for the horizontal force of the reaction force at point B, so that will be summation of forces horizontal equal to 0. So we have a component, horizontal component of 40 kilonewtons. So therefore you have 40 cosine of 35 degrees, then equal to RBH. So this RBH now is equal to 32.7566 kilonewtons. So therefore, our R's of B is equal to the summation of R's of BV plus R's of BH. And if we try to substitute the values, this gives us 59.076 kilonewton. So this is the shear force at point B. So therefore, for this one, the shearing stress at point B, we're going to have our formula shearing stress is equal to V all over A. So this is equivalent to shear force 59.076 all over the area, which is this 2 times, this is a double shear pi over 4 times 20 squared. So if we try to simplify this one, it gives us 94.02 megapascal. So that is for our shearing stress at this is double shear.